Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos important and interesting to your studies, also please don't forget to subscribe. This is a beam example 12 and I presented the solution by the matrix approach. And since high-tech calculators that are capable of solving four simultaneous linear equations are allowed in the Philippine Civil Engineer Licensure Board exams, so that's why I presented this problem with four simultaneous equations. By the matrix approach, compute all the vertical support reactions of the beam shown below. Modulus of elasticity 200 gigapascals, moment of inertia 500 times 10 to the 6 millimeter to the fourth, and the support downward movements are A 10 mm, B 18 mm, C 15 mm, and D 4 mm. So here is the given beam. So let's have our guide. Then we compute fixed moments, which consists of fixed moments due to the load and side sway moments. So let's just assume the direction of the fixed moment shown. If it does not conform to the assigned direction, then let's just make the direction negative. So fixed moment AB is negative 25 5 square over 12. That's the formula. Minus 6 EI. EI is 100,000, 200 gigapascals times 500 times 10 to the 6 mm to the fourth. Convert that to kilonewton meter square. So that's 100,000 kilonewton meter square. Since the rotation of the chord AB is clockwise, so we treat the delta to be positive from slope deflection uh, assumptions. So 10 to 18, so that means 8 mm downward, and that is treated as positive in the formula, side sway moment formula, negative 6 EI delta over L square. So negative 6, 100,000 delta is 0.008 meter or 8 mm divided by 5 square. Both are negative, so that means uh, fixed moments would be directed as shown. Negative 625 over 12 or negative 192. So it is 244.083 counterclockwise as shown. Then fixed moment BA is positive 625 over 12 minus 192. The result is negative. So let's just make it negative. And the direction is clockwise as shown. Then the fixed upward force FAR, considering AB summation moment about B equals 0. So FAR times 5 plus fixed moment BA, which is negative 139.917, equals fixed moment AB, which is 244.083 plus the moment of the load, 25 times 5 times 2.5. So the fixed force, upward force for AB is 139.3 kilonewtons. Then summation forces Y 139.3 plus FB left equals 25 times 5. So solving for FB left is negative 14.3 kilonewtons. Next, we could proceed to BC. Let's still assign the direction of fixed moment shown. So negative 34 square over 12, then minus 6 times EI 100,000. Delta this time is, since counterclockwise rotation of chord BC, so 3 mm, the difference is 3 mm, and 3 mm is treated negative because the rotation of the chord BC prime is counterclockwise. Negative 0.003 meter over L square 4 square. So it is negative 40 plus 112.5. The result is positive. So let's just make it uh, counterclockwise in that direction, and let's make it negative. Fixed moment BC is negative 72.5. The result is positive 72.5. We expect this to be in that direction, so we make it negative 72.5, and the direction is counterclockwise as shown. Then fixed moment CB is positive 40 plus 112.5, so the direction is correct and it is clockwise 152.5 kilonewton meter. Then solve for FB right and FC left. Considering BC, summation for moments about C equals 0, FB right times 4 plus 152.5 equals, because this is negative 72.5, equated to negative 72.5 plus the moment of the load, 30 times 4 times 2. So FB right is equal to 3.75 kilonewton. Summation forces Y equals 0. 3.75 plus FC left equals 30 times 4. So FC left is equal to 116.25 kilonewton. So these are fixed forces to be added after we computed the nodal global displacements. So we proceed to portion CD, and the rotation of the cord again is counterclockwise. The difference is 15 minus 4, 11 mm. So 11 mm is negative in the formula. So fixed moment CD is negative WL square over 20, and let's assume that's the direction. So fixed moment CD is negative 27 6 square over 20 minus 6 times 100,000 times negative 0.011 over 6 square. The first is negative, the second term is positive. So the result is positive, and since we anticipate negative in that direction, so since this is positive, it should be clockwise, and therefore let's just make it negative and assume counterclockwise. So fixed moment CD, the result here is positive. Let's make it negative, and this is the direction. Negative 134.733 kilonewtons. Finally, fixed moment DC is 27 6 square over 30 plus 550 over 3. So it's positive, so it is the direction, clockwise direction as shown. So combining, it is equal to 215.733 kilonewton meter. Then let's solve for FC right and FD left. Considering CD, summation moment D equals 0, FC right times 6 plus 215.733 equals negative 134.733 plus the moment of the load, which is 1/2 or 0.5 of 6 times 27. Then moment arm 2/3 of 6 is 4. So equals this moment here, but because this is negative, so we carry the sign, and plus the moment of the load, which is counterclockwise about D. Solving for FCR, FCR is equal to negative 4.411 kilonewtons. Then summation forces Y, negative 4.411 plus FD left equals 1/2 or 0.5 of 6 times 27. So FD left is equal to 85.411 kilonewtons. Then let's have the nodal forces. Imagine A is 1, 2, 3, 4. We only need the global displacements U2, U4, U6, and U8, which correspond to theta A, theta B, theta C, and theta D respectively. The global forces, nodal forces, would be the opposite of this direction. So if we treat clockwise as positive, then minus counterclockwise. If the result is negative, then that's the final global force or load. So 0, left of A is 0, then minus fixed moment AB, which is 244.083, so negative 244.083. So it is clockwise because the counterclockwise rotation is the globally universally accepted correct sign convention. So it is negative 244.083 or clockwise. Here, fixed moment BA is negative 139.917, then minus fixed moment BC, which is also negative, so negative 139.917 minus negative 72.5 or plus 72.5, the result is negative, and it is also clockwise. So that's 67.417. Again, negative 139.917, this one, because this is negative, and minus this value, negative 72.5, the result is negative. So that's why it is clockwise here at node 2. Then at node 3, fixed moment CB is positive 152.5 minus fixed moment CD, which is negative. So positive fixed moment CB 152.5 minus negative 134.733, that would be 287 point something positive, so it is counterclockwise, 287.233. Then finally, because this is clockwise and it is positive DC, so clockwise and make it counterclockwise because global forces are opposite to the nodal forces. So this is fixed moment DC 215.733 minus 0. So 215.733 minus 0 is 215.733 positive, so it is counterclockwise, opposite to that. So these are the nodal forces. Then let's set up, this is negative, negative, positive, positive. Let's set up the stiffness of member AB. So this is the stiffness of member AB. It is bounded by 1, 2, 3, 4. So 1, 2, 3, 4. The entries would be 12 EI. Let's just assume EI as 1. So we factor out EI over L cube. So 12 over 5 cube is 12 over 125. The next entry in this row is 6 EI. 6 times 1 over L square. 6 over 5 square is 6 over 25. Then this is the negative of the entry here, and we just copy this entry. For the next row, it is 6 EI over L square, so 6 over 5 square, 6 over 25. This is 4 EI over L, 4 times 1 over 5, so 4 fifths. This is the negative of this entry, and this is half of that entry, 2 EI over L, so 2 over 5. The third row would be the negative of the first row elements. Observe the negative of the first row elements, and the last row, fourth row, is just the second row with the second and the fourth entries interchange. So same, except that we interchange position the second and the fourth entry of that rows. So that's it. Then we proceed to the stiffness of member BC. So for member BC, Stiffness bounded by 3, 4, 5, 6. We have 12 times 1, EI is factored out. So 12 times 1 over 4 cube is 3 over 16. The next entry is 6 times EI 1 over 4 square, so 3/8, the negative of this entry, and we just copy that entry. Then 6 EI over 4 square, 6 over 4 square, 3/8. 4 times 1 over 4, 4 times 1 over 4 is 1. Then this is the negative of that entry, then this is half of that, of this second row entry. Then this is the negative of the first row, just like before. Then this is the second row with the second and the fourth entries interchange. And finally, for KCD, 5, 6, 7, 8, 12 times 1 over 6 cube is 1 over 18. 6 times 1 over 6 square is 1/6. Then the negative of 1 over 18, then this just copy 1/6. This is 6 times 1 over 6 square, or 1/6. This is 4 times 1 over 6, or 2/3, negative of this 1/6 here. Then 1/2 of 2/3 is 1/3. Then the negative of the first row entries. Then second row entries with the second and fourth cells interchange. So I hope you are able to remember the setting up of this stiffness for an element if it is still your first time. So we now have the global forces, and we are only interested of 2, 4, 6, 8, because 3, 1, 3, 5, 7 are not important, just the rotation. So these were the nodal forces from the preceding slides. Then we have 2, 4, 6, 8, 2, 4, 6, 8. So 2, 2, we have 2, 2 from member AB earlier, and it was 6 over, it was, sorry, 4 EI over L, so 4/5. So 4/5. Then 2, 4 is 2/5, half of 4/5. Remember, from stiffness of member AB. Then we have 0 for 2, 6. Then 0 also for 2, 8. Because it is between A and C. To A and C and A and D, they are not connected directly. So that's why we have 0, 0. Since the global stiffness or universal stiffness matrix is symmetric with respect to this diagonal, so we copy 0, 0 here. Then we have 4, 4. We have 4, 4 for member AB plus 4, 4 here is 1. It was 4/5. So 4/5 plus 1 is 9 over 5. So 9 over 5 here. We have 4, 6. So we only have 4, 6 here, which is 1/2. Only for BC. Then 4, 8. 4, 8 is none. So 0. So we copy 1/2 and 0 here. Then this is 6, 6. So 1, 2, 3, 4. So for AB, there's none. So 6, 6, we have 1 here and 1 plus 2/3. 1 plus 2/3 is 5/3. Then we have 6, 8. 6, 8. So 1/3. So we copy 1/3 here for 8, 6. And finally 8, 8, which is 2/3 here. So we can now compute these global displacements U2, U4, U6, U8, which correspond respectively to theta A, theta B, theta C, theta D, by the product of the inverse of this matrix and these global nodal forces. So U2, U4, U6 is 1 over EI times the inverse of this global stiffness matrix and these global forces. So the results using the calculator would be equal to negative 303.302 over EI, negative 3.603 over EI, 120.779 over EI, 263.210 over EI. Negative rotation means clockwise, and positive rotation means counterclockwise because the positive rotation is counterclockwise. The sign convention universally. Having found these global forces, we can now compute the member forces. So for AB, we have shear AB, moment AB, shear BA, and moment BA. We only consider elements of its elemental stiffness, which can be multiplied by this global displacements U2 and U4. So that's why we only consider 2 and 4, because for 1 and 3, the corresponding nodal displacements will be 0, so it's useless. So for instance, and the fixed forces, remember FAR is 139.3. Fixed moment AB is positive, and it is the positive of this value because this is the nodal global force, so which is clockwise, and the fixed force is counterclockwise, so that's why it's positive here. Then negative 14.3 for FB left, and 139.917 for the value here because I assume clockwise, but it was negative, so it is counterclockwise, so positive 139.917. So to solve for shear AB, for instance, we have 6 over 25 times negative 303.302 plus 6 over 25 times negative 3.603 plus 139.3. So we have the results. Then moment AB is quantity 4/5 of negative 303.302 plus 2/5 times negative 3.603 plus 244.083. So it is expected that the moment at A or moment AB is 0. So that's why it's 0 there. For shear BA, negative 6 over 25 times negative 303.302 plus negative 6 over 25 times quantity negative 3.603 plus negative 14.3, so 59.357. And finally, for moment BA, quantity 2/5 of negative 303.302, so cancel EI, plus quantity 4/5 times negative 3.603 plus 139.917. So it is 15.714. So the meaning of 15.714 is it is BA. So it is counterclockwise. Because it is positive. So for shear BC, moment BC, shear CB, moment CB, we only interested of the elements in columns 4 and 6. And these are the global displacements, U4 and U6. And these are the fixed forces. So same explanation as above. So I don't need to explain it anymore. You just follow the explanation of the first. So the results would be the following. So we have, that's why moment in BC is the negative of this moment here. It agrees. Then moment CB negative 33.523. Then finally for shear CD, moment CD, shear DC, and moment DC, we expect moment DC to be 0 because the moment at D is really 0. So we are only interested of elements in column 6 and 8 because this corresponds to U6 and U8, and these are the fixed forces. So we have these results. So from here, we can now compute the vertical reactions. RA is equal to AY, and it is shear in AB, which is 65.643. Then for RB, it is the shear in BA plus shear in BC. Shear in BA is 59.357 plus shear in BC, which is 47.693. So 59.357 plus 47.693, that's RB. And it is equal to 107.050 kilonewtons. R sub C is shear CB plus shear CD. Shear CB 72.309 plus shear CD 59.587. So add 72.309 and 59.587, that's 131.896 kilonewtons. Finally, for reaction at D, it is just shear DC. And shear DC is 21.413. So it is 21.413. So that's it for this problem. I hope that you were able to follow the explanations and the solutions by the matrix approach.